for taking the time to review the thesis and for being here today. My name is David Rodriguez, and over the past 3 years, I've been working on high-speed lunar exploration, in particular within the field of wheeled mobile robotics. So for today's presentation, I'm going to start by briefly answering two questions. What and why? What are the challenges associated with lunar locomotion? And why increasing speed is a relevant problem to be solved for the case of the robotic exploration of the moon. Then I'll move on to explain what we knew about faster off-road locomotion, both here on Earth and on the moon. And this broad introduction will allow me then to present the highlights of my work in the two main areas comprising locomotion, which are traction, that will be chapter 3, and suspension performance in chapter 4. Using all the experience and these new findings, in chapter 5, I'll present the design of a new rover prototype intended for faster lunar mobility studies. And I will end this presentation with a summary of the main contributions of my work to the topic of rapid lunar locomotion. So let's start then with what's the problem with lunar mobility and why we need robots capable of moving faster. So if we strip the tasks a planetary robot or a rover has to perform down to the very basic, it would be to get from point A, usually a lander, to point B. Now, yes, there are many experiments to be conducted and measurements that need to be recorded in between those 2 points, but really there will be no mission for these robotic scientists without the capacity to travel. And it is exactly in this apparently mundane task where some of the most challenging problems lie. So my goal for this project has been to understand the effects of moving from A to B at speeds that approach 1 meter per second and to develop solutions to make that journey possible, successful, and safe. And for that, I needed to understand the effects of increasing speeds in the two aspects I mentioned before, traction and suspension performance. But why is this type of studies a challenge? Well, I've identified 3 main reasons why that's the case. The first one is that exploration is by nature characterized with a high degree of uncertainty. In the case of the moon, for instance, information is quite asymmetric or non-homogeneous. We don't know whether the state of polar regolith, for example, would resemble that of the equator, given the lower temperatures and the less severe thermal cycles of high-latitude regions. The second reason lies in the impossibility to simultaneously reproduce and test on Earth the full scale of environmental conditions robots will experience during a mission. And this is particularly relevant in the case of high-speed locomotion, since, for instance, the gravity scaling technique used to test planetary rovers here on Earth, by which its ultimate weight is simulated degrading the mass of engineering models, could not be used the moment inertial effects and dynamics start to dominate the behavior. So verification and validation across different gravity fields prior to a mission becomes increasingly difficult. And this brings me to the third problem associated with extraterrestrial ground mobility, and one of the major topics of study in my work, which is the complex nature of the interaction with soils. I'm sure you've seen this sequence of images many times of NASA's Spirit rover desperately trying to free itself from a bank of unconsolidated sand. The challenge here is that we are still working toward gaining the understanding that allows us as engineers to develop tools that help us predict the outcome of these sort of interactions to avoid precisely what happened to Spirit. So with all these constraints already present for the case of rovers whose speeds rarely surpass 5 centimeters per second like those on Mars, why consider developing robotic systems capable of traveling 20 to 100 times faster in an environment like the moon where gravity is just a sixth of Earth's? And there are multiple reasons why you would want to make your robotic systems faster. Just as an example, there is a set of conceptual missions similar to the one you see on the screen, currently being drafted and discussed among space agencies for the exploration of particular regions within the lunar pole. This is a 37-kilometer traverse comprising 5 sampling points through the Schrödinger basin in the lunar South Pole. And it is expected that these new missions will demand the capabilities of faster lunar robots. But why is that? Well, the lunar poles have become the most sought-after regions of the moon by governments and private corporations due to its scientific value and the potential richness of its resources, primarily water ice and other volatile compounds. In the poles, the sun barely rises above the horizon due to the low obliquity of the moon, making illumination conditions very challenging for navigation systems. Also, some of these regions, the window of exploration is linked to just 7 days of sunlight for every month, and there is a high percentage of areas that are kept in complete darkness, what we call PSRs, or permanently shadowed regions, where a higher amount of these valuable compounds are actually expected to be found or trapped in. So if we combined shorter days, the lack of sunlight, longer traverses like this 37-kilometer journey with 2 particular goals, one, the maximization of the return on investment for the mission, and that could be scientific or commercial, and to the avoidance of heavy nuclear decay units, well, then faster locomotion becomes a potential enabler for these missions, getting in and out of shaded areas and simply getting to those sampling points as fast as you can so that more time can be devoted to the science. In this study in particular, the authors estimated that a speed of at least 50 centimeters per second would be necessary for the mission to be completed within the 10-day window available, and allowing enough time for the scientific task to be conducted at each sampling point. So now that we have an idea of the challenges lunar locomotion studies faced and why upcoming missions, specifically those targeted at the poles of the moon, may require faster rovers, the next aspect we need to look at is what do we know exactly about what it takes to move faster on the moon? And it is imperative that we first turn our attention to terramechanics. Terramechanics is the branch of science devoted to the study of the interaction of vehicles and machines with soils. And one of the theories most widely used within the realm of off-road locomotion has come to be known as the Becker method. It's a simplified, closed-form, semi-empirical model used to predict the vertical loads acting on the soil as a result of the movement of a large wheel. This model has been then expanded by many authors, including Wong and Rees, giving rise to the two equations you see on the screen, the pressure sinkage and the shear stress-strain relationship. The important thing I would like to focus on here is not necessarily the equations, but the fact that this theory that initially was meant for tanks and big military trucks being driven across muddy grounds, it has now been applied to planetary robots orders of magnitude smaller, lighter, and slower, operated on soils with close to none, as far as we know, organic matter. So predictions through these equations are not necessarily our best chance at understanding the problem and predicting the outcome of robotic mobility and lunar locomotion. Some of the most important limitations of Becker-based models include the lack of information as to the physics taking place in the interaction with soils, the need to perform an experimental characterization of the state and the properties of the soil on which the rover will ultimately operate. And as you can imagine, this dependency on empirical data hinders the validation of these models, particularly in the case of planetary exploration, where data is often scarcely available. Also, its bidimensional representation and the oversimplification of the wheel geometry and the terrain is a big limitation. But for our case, the biggest disadvantage imposed by the use of Becker-based equations resides in their inability to take into account dynamic effects. We know already from studies conducted in the field of soil mechanics that pressure and sinkage are affected by the rate of penetration. They are affected by dynamic effects. The Becker model and those that are based on it assume the interactions of wheels and soft grounds occur under quasi-static steady-state conditions, making these equations independent of the potential effects of caused by soil strain rates, inertial effects, or transient operations. But what about evidence from previous missions to the moon? We've been to the moon already with rovers way faster than today's Martian rovers. Two missions, the Soviet Luna 17 and 21, featured Lunokhod 1 and Lunokhod 2, a pair of 800-kilogram, 8-wheel rovers remotely operated from Earth with a top speed of 50 centimeters per second. And of course, the last three Apollo missions, which featured the well-known lunar roving vehicle, a piloted lunar vehicle capable of traveling at a speed of up to 5 meters per second. Unfortunately, none of these two vehicles counted with sufficient telemetry on board for us to derive definite conclusions as to the performance of these vehicles when they were moving faster under lunar conditions. However, by looking at the footage and by closely examining the post-mission reports, we can extract some key lessons to be learned. So one of the first things that becomes evident from the footage of Apollo, and also one of the aspects the Apollo crew remarked in their reports, is the tendency of the suspension to constantly bounce. These instabilities became prominent at higher speeds to the point where it prevented the astronauts from driving at speeds above 2.8 meters per second, with the wheels reported to consistently lose contact with the ground at speeds above 1.4. This excessive bouncing of the suspension decreased traction, reduced the stability of the rover when negotiating slopes, and diminished the capacity to brake and turn, with braking distances reported to be almost twice than those required on Earth. All of this limited the average speed of the three missions to about 2 meters per second. And as with the case of unconsolidated Martian soils, the entrapment of the wheels was also a major concern, primarily when overcoming slopes. Another aspects less relevant to our studies but equally important were dust, which was reported to be also one of the major factors to take into account, and ambient lunar factors, the freezing temperatures, the harsh illumination conditions, the lack of contrast and blending of the horizon and the surrounding obstacles made operating these vehicles at high speed ever more complex. So in light of the inconclusive evidence that existed in relation to the locomotor performance of planetary robots when operating at higher speeds, the first thing I tried to understand was how speed affects traction. And for this part, I had two main objectives. First, I wanted to understand how speed was affecting tractive performance metrics, namely Rover pull, wheel sinkage, and tractive efficiency. And second, I wanted to obtain a numerical and visual proof of the variations in the dynamic interactive behavior when operating over different types of soils. So in order to conduct these experiments at speeds up to 1 meter per second, I partnered with the Institute of System Dynamics and Control of the German Aerospace Center, where there is an ambient-controlled automated facility called the Trimechanics Robotics Locomotion Lab. This facility, unlike conventional single-wheel testbeds, makes use of an industrial robotic arm and an extensive sensor suite, which we use to constantly monitor the performance of the wheel over a run distance of 3 meters. A hybrid controller was used to vertically impose the required wheel load and to control the speed of the robotic arm longitudinally. So this way we could recreate varied sleeping conditions. And here you can see the two end effectors we used. The one on the left, it contained the drivetrain, which is what we used to operate the wheel. And the second one on the right was used to condition the ground before every experiment. So we conducted 500 different tests, collecting, as far as I know, one of the most extensive data sets that exist to this day on the effects of speed on tractive performance for non-pneumatic wheels. We operated different types of wheels commonly used by planetary rovers over 2 different types of soils. For most of the tests, we used a cohesionless olivine-based sand, codenamed RMCS 14. And then we also tested the performance over a more challenging type of soil named RMCS 13, which is a calcite-based silty soil, very fine-grained, soft, and slightly cohesive. For every case study, the speeds tested went from 1 centimeter per second to 1 meter per second, and these were all forced sleep tests, and for all of them, we used a wheel load of 100 newtons. So what is it that we found? Well, I conducted 2 types of data analysis. The first one looking at how Drovel pull coefficient, wheel sinkage, and tractive efficiency, represented here from left to right, evolved with increasing speeds in the x-axis for 2 sleep ratios, 20 and 60%, representative of low and high sleep conditions. Here you can see the results for the case of a 25-centimeter rigid wheel with 12 grousers, but similar trends were observed in the other 3 cases. As you can see, tractive performance was clearly affected by the speed of the wheel. Drovel pull coefficient and efficiency decreased, while sinkage increased with increasing speeds for both 20 and 60% sleep. The lowest impact on performance of just about 7% relative to a speed of 1 centimeter per second was experienced for speeds up to 20 centimeters per second. And beyond this point, an apparent increase in soil fluidity was observed, which may indicate a dominance of dynamic effects in the interaction, and performance starts to degrade at a higher rate. The second type of data analysis that I conducted consisted of analyzing the evolution of Drover pull coefficient and the tractive efficiency, but this time across the full range of sleep ratios, represented now in the x-axis. 2 interesting observations to note here. The first one, if we look at the evolution of Drover pull with sleep ratio on the left side, we can see that Drover pull increases for increasing sleep ratios at lower speeds. And this is something that we knew already. We expected from low speed test results available in the literature. But the tendency changes and starts to plateau at speeds above 20 centimeters per second, with a sudden loss of traction when high speed and high sleep ratio is combined. The second interesting observation, if we look now to the right side graph, is the tendency of the sleep ratio at which maximum efficiency was reached to increase with increasing speeds. At low speeds, maximum efficiency was often reached at 10% sleep, whereas at 1 meter per second, the maximum efficiency was recorded to be reached at almost 30%. With regards to the variations in the dynamic interactive behavior, it was much harder to manipulate and drive over the finer and slightly cohesive calcite soil, which is the one you can see in the video now. Above 10 centimeters per second, we experienced almost a complete loss of traction due to the low bearing capacity of the soil. And as you will see in a few seconds, the macroscopic behavior of the different soils we used show clear variations. The olivine-based sand, which is the one on the right side of the video, displayed an increased fluidity when subjected to high strain rates, something that was not observed in the calcite, with bulldozing effects being much more predominant in this second case, as you can see here. And lastly, the flexible wheel displayed the best performance along the full range of velocities. Measurements recorded at 1 meter per second with the flexible metallic wheel displayed over 2 times higher Rover pull and tractive efficiency and about 18% lower sinkage at 20% slip compared to a rigid wheel of similar characteristics. So once I understood how a speed played a role in the tractive performance of rovers operating up to 1 meter per second, the second aspect I was interested in was the effects of speed on the suspension performance. The core premise for an optimal suspension design in planetary robotics is it has to be mechanically simple and potentially passive. Most planetary rovers make use of passive free balancing suspension configuration similar to this one. This is called the rocker bogie suspension, initially designed by NASA for Sojourner during the Mars Pathfinder mission, although Sojourner had it with it reversed, the bogie was in the front. The simplicity of passive suspensions becomes almost a necessity in space, given the limited volume and power budget of space activities. And the dependency of these suspensions make them great for obstacle negotiation, terrain compliance, and vehicle stability at very low speeds, but not so much for mitigating impact loads and vibrations and maintaining proper stability of the rover at higher speeds. So in order to understand the limitations of passive suspensions, but when applied to smaller four-wheel rovers operating at higher speeds, I needed to turn to multi-body dynamic simulations, where in combination with high-fidelity physics engines, I could actually observe and monitor the dynamics under a virtually simulated 160 environment. To develop the different modules that I required for my research, I decided to make use of a commercial software called Virtual Robot Experimentation Platform, or VREP, although recently has been renamed Coppelia Sim, in combination with the dynamic physics engine Vortex. So using this platform as a baseline, I developed 4 different simulation modules to simulate extreme situations the lunar rover will encounter once on the moon. This included traveling at 1 meter per second when overcoming large rocks, climbing steep slopes, or suddenly encountering an outcrop. To simulate the frictionless character of lunar regolith, which is often the most complicated part to simulate accurately, I opted for a simple Coulomb friction model with an isotropic friction coefficient of 0.4 for the interaction between the wheels and the soil. This provided a range of slip ratios between 5 and 35% for these situations, and I knew this was an oversimplification of the real situation, but it was a trade-off I needed to make in favor of shorter turnaround times in the simulations, and also knowing that I would compare all the different models against the same simplified baseline. And then what I did is I modeled a multi-body dynamic system of a rover we had in our lab at the time called Eldorado 2, which is the rover you can see in these images, a 4-wheel, 19-kilogram rover with passive rocker arms and rigid wheels. So what I wanted to observe was the variation in the performance when energy dissipation devices, in this case passive springs and dampers, were introduced in the design under different suspension configurations. So using the same mass distribution, sizes, and suspension layout, I defined 3 different configurations. A conventional dependent rigid configuration. This simulated the use of free balancing rocker arms. An independent elastic configuration. In this case, the rolling of the rocker was locked, and a spring damper system was introduced between the wheel hub and the end of the rocker arms. This configuration simulated the double wishbone we use sometimes in ground vehicles here on Earth. And lastly, I devised a new configuration in which the previous 2 were combined into what I named mechanically hybrid suspensions. The performance was evaluated in terms of success in overcoming the obstacle or the slope, maximum vertical load to the suspension arms, and maximum vertical accelerations measured in the chassis. So unfortunately, I don't have enough time to go over every single case. I'm going to showcase one of the most extreme cases, which was suddenly confronting an outcrop at 1 meter per second. So if we pay attention to the videos on the right side, you can see the violence of the situation. When we simply use conventional rocker arms, the wheels lose contact with the ground, and we almost completely lose control of the rover trajectory. There is a high risk of damage, not only of the wheels and the suspension arms, but also of the electronics and the optics housed inside the main body of the rover. If we look now to the graph on the left side, simply by adding springs and dampers, already substantially decrease the effects of impact loads. But if on top of that, we introduced a dependency with the MH configuration, we achieved a 95% reduction in maximum vertical loads and almost 63% reduction in torque when compared to the dependent rigid case. And here you can see the difference. Unfortunately, I cannot loop the video on the bottom part. I'll click it a few times. So now it's playing the case of the mechanically hybrid suspension configuration under the same exact conditions. As you can see, much less movement of the rocker arms can be observed, together with an overall gain of stability in the motion profile of the chassis and in the trajectory. On the left side, we can see the recordings of the IMU placed inside the body of the rover. And here as well, we can see a significant mitigation of the vibrations. Here we have a table that gathers all the results from all the different cases. And the mechanically hybrid configuration successfully reduced the detrimental effects of an irregular terrain in 62% compared to the dependent rigid and 43% compared to the independent elastic configuration. Okay, so with everything we learned so far about what is required to travel faster while guaranteeing safety and good performance of the rover, we decided to design a new rover prototype that makes use of this type of chassis configuration, and we called it Explorer 1. Based on the chassis of the old Eldorado 2 platform, Explorer 1 was designed as a teleoperated 23-kilogram rover, drivable at speeds up to 1 meter per second. It has 4 independently driven and steerable 20-centimeter wheels. We also equipped the rover with 2 onboard computers, navigation cameras, and a LiDAR so that future students can work on increasing its levels of autonomy. And it has a suspension system that is based on the principles of the mechanically hybrid configuration. So the mechanically hybrid configuration was realized reusing the old rocker arms from the older platform that provided a large travel range of about 250 millimeters. Attached at both ends, we included independent double control arm elastic suspensions, providing an additional compliant travel range to the wheel of about 35 millimeters. Here is a detailed schematic of the elastic part of the suspension. 2 control arms were used to maintain constant camber angle during wheel travel. In addition, we added the possibility of for the dampers to slightly change their position with different mounting points, so that in this case the stiffness of the lower travel range of the suspension could be farther tuned. And we used the harmonic drive of the steering motors as the connecting part between the rocker arms and the elastic suspension. And as I remarked in the thesis, this configuration favors the modularity of the design. It's very easy to adapt this particular configuration to a 6 or an 8-wheel chassis, and also even to adapt it to stowable configurations by the addition of deployable motors. So then what I did is I developed a dynamic model of this design in CoppeliaSim using the same framework as before. I conducted a simulated performance evaluation under lunar gravity, which you can find thoroughly explained in the thesis. And in addition, as a case study, I developed a virtually simulated lunar mission, which is what I'm about to present, consisting of a 20 by 15 meter virtual lunar environment where the rover was commanded to follow an 18-meter traverse formed by 4 stages. So the first part of the mission was the rover needed to egress from a hypothetical lander, just like any real mission. This was done through 3-meter ramps deployed at 15 degrees. The commanded speed here was just 5 centimeters per second to ensure safety of both the rover and the lander. The second stage starts the moment the front wheels touch down on the ground. To touch down follows a 16.5-degree incline, while the rover was commanded to accelerate up to 50 centimeters per second. You will see that in a second. Because of this, at the summit, the front wheels briefly lose contact with the ground for about 1.3 seconds, incurring the highest acceleration experienced by the chassis of 0.46 Gs. Following the initial climb, the driving motors were commanded to suddenly brake and slow down at 10 centimeters per second, and the steering motors were commanded to make a 90-degree turn to the left. Here we use a simple 2-Ackermann steering control. Once the cornering maneuver is completed, the rover is commanded to face the most challenging part of the mission, which is an extreme 9-meter climb reaching top speed that is 1 meter per second at the top over a highly irregular terrain, which has a maximum inclination of 21.5 degrees. As you could see, some of these situations, like heading toward the steeper incline at top speed, comprise quite an unlikely scenario for a fast-moving rover operating on the moon on a real mission. But even under these conditions, the rover suspension was capable of maintaining the body stable, helping the rover reach the goal and successfully accomplishing the mission. The maximum vertical load recorded on the suspension was 58.5 newtons, and vertical accelerations were maintained always below 0.5 Gs. So despite the successful outcome of the simulation performance evaluation, a potential improvement of the current design would be the combination of the mechanically hybrid suspension with compliant wheels. So on the one side, the dependent part of the suspension efficiently distributes the weight among the different wheels, increasing stability, particularly at lower traveling velocities, and providing the high travel range necessary to negotiate large obstacles. Then an extra degree of compliance is achieved by the use of independent springs and dampers. These provide each wheel with a lower passively controlled travel range designed to attenuate vibrations and mitigate the detrimental effects of shocks and impacts while isolating the chassis. And then if on top of all this, we add the flexible wheels, this could potentially improve the performance in at least two ways. One, flexible wheels provide a larger contact area, adapting it to the regularities of the terrain, which diminishes effective ground pressures and subsequently decreasing wheel sinkage and significantly improving tractive performance, as we already saw in chapter 3. And secondly, the flexible wheels have the capacity to mitigate non-vertical loads, such as those inflicted on the wheels during the first instances of negotiating a very large obstacle. Another interesting aspect that should be kept in mind, as I mentioned at the very beginning of the presentation, is the effects of gravity on dynamic motion. As an example, here we have the pitch motion profile when driving across a 15-degree slope over a distance of 3 meters. As we can see, clear variations can be observed across different gravity levels, and this is expected when you use the same exact rover, same size, mass, and suspension configuration. So in order to approach testing on Earth, we have several options. One would be to offload gravity, creating a counteracting vertical force. It would be the best option for simulated dynamics, but it has the downside of being limited in size and distance traveled. Another potential solution would be to scale the testing model of the rover or its suspension configuration based on dynamic scaling principles. And one example of those would be the use of the dynamic similarity hypothesis, so that the motion of both the rover on the moon and the model on Earth experience a similar ratio of inertial forces to gravitational forces. This is what's called the Freud's number. In this, if this dynamic scaling method is applied, for instance, to the harmonic motion of the springs of the suspension without necessarily changing anything else and neglecting the nonlinearities within the system, the motion profile that we obtain becomes much similar to that of the moon, of the real rover on the moon. Although in this case, inflicted forces would vary. So to end this presentation, I would like to address the main contributions of my work and key milestones achieved throughout this project. The prime objective of this project was to shed light on the potential application of high-speed mobility to future lunar missions. So the first thing I established was a collaborative framework. I was very fortunate to count with the support of the European Space Agency and the German Aerospace Center, collaborations that would not have been possible without the support of Tohoku University's GPMEC program. So together, initially, we drafted the needs and objectives for this project. Then I examined the body of knowledge available at the start of the project with regards to the off-road locomotion performance, both here on Earth and also for previous moon missions, and realized that the existing evidence was far from being conclusive. So as a consequence, my first objective then was to conduct my own experimental evaluation on the evolution of tractive performance metrics with speed, and within conditions that better represented those of planetary robots. This resulted in a set of recommendations and guiding principles to maximize performance under high-speed conditions. And some of the most relevant findings, just to summarize them, include the degradation of performance for speeds above 20 centimeters per second. This may be due to a transition in the physical phenomena dominating the interaction between the wheel and the soil. And although this varied depending on the soil we used, and the sleep ratio with maximum efficiency was reached, which appeared to increase with increasing velocities. So after this, in order to fully understand the consequences of reduced gravity vehicle dynamics, I needed to move from independent wheel-soul interactive response to the full vehicle response. So I developed a series of dynamic simulation modules where I conducted a comparative study introducing energy dissipation devices to the suspension configuration of a lightweight 4-wheel lunar rover. This resulted in the proposal of a novel configuration named mechanically hybrid suspension configurations, and appeared to outperform, based on the simulation results, more traditional passive configurations under a variety of scenarios. And lastly, the principles behind this new configuration were then translated into the mechanical concept design of a new 4-wheel lunar rover that we named Explorer 1. I also addressed the possibilities of combining the MH configuration with flexible wheels and potential solutions to the gravity scaling problem. And as a final case study, I characterized the performance of this new suspension design under a virtually simulated lunar mission in which the rover was proven successful in accomplishing the goal and maintaining stability and good performance even under extreme terrain and operational conditions. So that's all from my side. Thank you very much for listening, and I'll gladly take any questions you have. Thank you very much.
Okay, David, thank you very much for your presentation. So now it's the time for the questions and answers. So the first, I would like to invite the committee members to give a question to him. So who can go first? Maybe Michel. Yeah, I appreciate that you joined this session from Netherlands. And yeah, if you have any question to him.
Thank you, Professor Yoshida. Thank you, David, for your presentation. I've had many opportunities to ask questions in the past, so I have no further questions left at this moment. I'd like to give my time to somebody else. Thank you.
Okay, thank you very much. So there are Professor Hirata.
Okay, thank you very much for your interesting talk. So I also asked you many questions in the previous defense, but I have a small questions. So in page 38, so you conduct a simulation. So, but I'm wondering about a lot of vibration in the for the vertical load and G-force acceleration, I think. So why this kind of vibration is occurred? So I think, so I cannot follow the information about sensor. So what kind of sensor is used and why this kind of vibration is occurred?
So these results are output from the software. So there is no like real sensor used here. And the vibrations may be due to two things. One is because the wheels are modeled with the grousers. So, and the soil is not simulated as a discrete material, it's modeled as a continuum. So then you have those vibrations generated by the contact of the grousers with the ground, with the simulated ground. And the second is just the inaccuracies that the measurements from the simulation have by nature. So that's why we see a lot of vibrations, and this is raw data. So this is obviously unfiltered raw data. So that's why we see a lot of oscillations and vibrations.
Okay, I understand that there is a grasser, so that there is a vibration. Okay, well, thank you very much. And I have another question about future work by extending your research. So I think this is a very nice simulation. So in the static, so if the rover speed is very slow, we don't concern about the dynamic behavior of the system. But in this case, we have to consider dynamic behavior. So in the case of the automobile car, we have to consider the vehicle stability control. So for example, in sometimes we have to consider the drifting of the system, drifting of the vehicle. So or we have to reduce the drifting behavior of the vehicle in the real vehicle. But in the case of the this kind of rover on the moon, do you have to consider about the drifting or reducing this kind of behavior? So I think you can control the whole wheels so that you can control the more complicated motion of the vehicle. So what do you think about the future expansion of this motion control, dynamic motion control of the rover?
Yeah, that's a very interesting question, and I don't have a clear answer. What I know is that it depends a lot on the characteristics of the rover. So, for instance, one of the lessons that we learned from Apollo missions, they could control the position of the four wheels. So they could steer the four wheels. And what they reported is that it was easier for them to reduce that drift and control the vehicle when they could only use front steering method instead of being able to control the four wheels. So that's, let's say, the only clear evidence that we have of what could potentially work best. Now, of course, this was a piloted vehicle, so we don't know. I'm assuming that, of course, for the case of a four-wheel rover, there will be a trade-off to make, and maybe using the 4 steerable wheels at lower speeds and then at higher speeds for small deviations, just use the front wheels with a 2-steering method. I think that would be the best option, and then we can always. I know that from some low-speed control methods using 4 wheels just to control the trajectory with the front wheels and avoid the slippage with the back wheels. So there are many different options. That's why it's hard for me to give just one answer. Sorry.
Oh, okay. Thank you very much. So I think this is a very interesting presentation. Thank you very much.
Thank you, Professor.
Yep. Thank you very much, Professor Hirata. So then I'd like to invite Professor Takahashi for his questions.
Okay, thank you very much. Thank you very much for your excellent presentation. So I want to ask you a very basic question. So if the vehicle speed is increased, I think there are several advantages. But on the other hand, how do you think about disadvantage when the vehicle speed is increased?
Well, again, it depends on how do we frame that question. So if we talk about autonomous rovers, a big disadvantage, so I've looked only at locomotion, then we have to look at navigation, and that's a completely separate problem, because then you need your control algorithms and sample rates need to be fast enough for the rover to make decisions on its own when it's moving that fast. So that's one of the biggest disadvantages. Then the problem is that we don't really know. So it's always a higher risk to move at higher speeds, because as happened with the Apollo mission, it could be that once on the moon, the side-to-side traction that we have moving faster is way lower than what we expected. So those are 2 potential downsides. Clearly, the first one that I mentioned with navigation systems not being capable to keep up with the pace of the rover is a big problem. Although we have solutions here on Earth with autonomous vehicles, it's a completely different story when we translate that to a limited computational and power rover. So that will be my answer to that.
Okay, thank you very much. And I want to ask you another questions about the control of the vehicle. So in order to control the vehicle, then do you need the information on the soil? For example, the cohesion or angle of internal friction or density of the soil or something?
Well, you don't necessarily need it. It will definitely help if you have it. Depending on the level of prediction that you want to have in your navigation algorithm. So for control, you don't necessarily need it. Of course, more data in the feedback loop is always welcome. But in principle, you don't necessarily need it. It depends on the type of study you want to conduct. But for control, I would say that you probably don't need it.
Okay, thank you very much. Okay. 以上です。
Thank you, Professor.
Okay, yes, thank you very much. So it's almost exactly the time to close, but yeah, we don't have any scheduled presentation after this. So taking this advantage. So if there are any questions from the audience, yeah, I'd be happy to accept 1 or 2 quick questions, if there are any. No, if you have a question, please say something fast. No question.
No.
Okay. If oh, okay. Yes. There was one student Andrew that yeah, he might have some question, but unfortunately we couldn't listen his voice, and so yeah, and yeah, I'm sorry that we will skip his question. But the other anything? Okay, yeah, he typed in the question in chat field, so just I need to bring up. So why do we switch to 4-wheel rover for the high-speed rover application?
Right. So, where in our case, we have always worked with 4-wheel rovers, so that's one option. Like it is what we have, what we had at the time. Although I would say that it just makes things easier. So there is already an inherent risk at moving at higher speeds, and it's potentially easier to operate when you have a 4-wheel configuration compared to a 6 or an 8-wheel configuration. But there is no, I haven't done a study of pros and cons of using a bigger configuration. So we use it initially for convenience. Yeah, thank you for the question.
Yeah, actually, that the 4-wheel designs was used in Apollo roving vehicle, and then yes, most of the today's motor vehicles, and but yeah, for the one side, the NASA's Mars rover, they have 6 wheels, and the Soviet, the Lunar had 8 wheels. So yeah, there are a number of design options. So there are some as a future study, the comparative study of the pros and cons, or also some criteria on the choice of the number of the wheels. That could be a very interesting topic. So. But I believe that David made a very good the fundamental framework to discuss these kind of things. So as a future topic. Yes, and there are the traction and the sinkage and the load distribution. There are a number of the issues. Yeah. So then other and another question maybe and that this will be the very last question in this session. So if there's nothing, yeah, let me close, propose to close this session. And thank you very much for David, first of all, for a good presentation. Then for the number of the audience who joined this session. So now we will move on the committee member discussion. So committee members, please remain in this the meet online. So then I request the others would quit from this session. So again, thank you very much for your participation.
Okay. Thank you, professors. Thank you, Michel, and thank you, everyone, for joining. Yep. See you. Bye-bye.
Okay. Goodbye.
吉田先生、岡部です。退出していいんですよね、僕は。
はい、はい、どうも、ご参加ありがとうございました。
はい、失礼します。
はい。Okay, now, there's still one, the maximum, and I hope you to quit from this field. Okay. Now, yes, we have only the committee members. Okay. So there are yeah, in the tradition, yeah, I'd like to listen to all the committee members' feedback, opinion, and the question is sometimes very simple. Yeah, do you propose that he will pass the final examination? And please answer yes or no. In case of the no or questionable, and please give us a comments on the question. So maybe in this the online conversation, maybe I'd like to ask each by each. So then I'd like to ask Michel first. Do you agree for him to pass the examination or not?
Yes, indeed, I do.
Okay, great, thank you. So then Professor Hirata?
Yes, I agree to pass.
Okay, and Professor Takahashi?
Yes, of course, I agree.
Okay, yeah, thank you very much. So then, yeah, our conclusion is very simple and clear. Then Mr. David Rodriguez should pass the final examination. Then he will, the PhD degrees will be awarded. And so then I will take necessary action to authorize this decision. So thank you very much for your participation. And then that's all. And so again, Michel, I really appreciate that you did accept David for his long-term internship and giving him an opportunity to work together with your team and also coordinate the experimental campaign with our colleagues at DLR in Germany.
Okay, yes, thank you. Thank you very much, Professor Yoshida.
Yeah, thanks so much. And please say hello to Jean Franco and then our colleagues at ESTEC.
All right, I'll do so.
Yeah. Thank you, and thank you very much, and goodbye.
Goodbye.
Goodbye for now.